Welcome. Welcome to this session on pharmaceutical analysis. Today, we are going to discuss about the errors and types of errors and what are the source of errors. I am Dr. Ahmed Nawaz Khan. Errors. These errors, they are the uncertainties in the result of an analytical method. When we get the uncertainties in the analytical result, this can be the error. These errors can be avoidable errors or unavoidable errors. During the laboratory testing, the need of accuracy in the result is an important issue. The most important aspect of the job of the chemical analyst is to assure that the data and the result that are reported, they must be of maximum possible quality. These errors, they are avoidable and unavoidable. These avoidable errors, they may arise from avoidable sources such as contamination, wrongly calibrated instrument, reagent impurities, instrumental malfunction, poor sampling techniques, and even the errors in the calculation. When the error arise from unavoidable sources, then these unavoidable sources result, they are known as bias. So what actually the definition of this error? In pharmaceutical analysis, the difference between the true or standard value with the observed value, the observed value which we get during the practical, during the experimentation, and during after the procedure. So the difference between the true or standard value with the observed value is known as the error. In this, there is a degree of uncertainty that is associated with every measurement, and and one can do its his best decrease this uncertainty to an acceptable value by avoiding these errors. While doing these pharmaceutical analysis, there may be uncertainty which is related with measurement, and it is because of minor errors that may happen in various stages of pharmaceutical analysis. Thus, therefore, analytical result is considered as an estimation of the true value and the content of analyte in the sample under consideration. It is important to decrease these uncertainties to a minimum level and to get the maximum possible quality results. So how we calculate these errors? So you can see there is a formula. Error is equal to true value minus observed value. This observed value we get after the experimentation, after the practical. This is the result, actual result value. So we can find that what was claimed in a sample and what we got. The true value, it is the claimed, and the observed value is the practical value, is the result value. So then we get the errors. Now, how much percentage error is there in the claim value and the observed value? That can be calculated by true value minus observed value divided by true value, the whole multiplied by 100. Now, what are these types of these errors? Now, these errors, they are of various types. They are determinate errors, there are indeterminate errors, absolute and relative errors, measurement errors, and accumulated errors. So now let's discuss what are these two determinate and indeterminate error. They are the most relevant types of error. So let's discuss these types of errors. So the first is determinate errors. These errors, they are determinable and presumably can be either avoided or corrected. These are can be avoided or corrected. Such type of errors, they are also known as systemic errors. These errors, they are well known by the pharmaceutical analysis, just like instrumental errors. Before we start working on an instrument, the instruments must be calibrated. So if the instrument is not working properly, analysts obviously know that my instrument is non-calibrated. In case of non-calibration, that means it's not working properly. The analyst knows that there are chances of getting the errors in the result. So in this instrumental errors, these errors they are occurred due to the use of the defective and non-calibrated equipment. So, and it is very common to all instruments due to their limited accuracy. This calibration of an instrument is one range may not be valid for entire range. For example, we have a pipette and this pipette is used to transfer the 10 ml, but it is taking up slightly greater volume. For example, 10 to 10.06 ml. Now, why is this so? It is because pipette was not calibrated, due to which it will give a greater volume, that is 10.06 instead of 10.10.0 mm. So this will give rise to a systematic error, and this error can affect all pharmaceutical analysis during which this uncalibrated pipette has been employed. Second is personal error. Such type of error is exclusively caused by the personal mistakes, and they are the closeness of the analyst. These can be reduced by experience. For example, mistake of the analyst during reading or calculation. These are some of personal errors. Operative errors. These errors, they are physically in nature and they occur when an appropriate analytical technique is not followed. The most common example of this operative error is the transfer of the solution, incomplete drawing of the sample, or some mathematical errors. So these are some of the operative errors. Reagents error. These type of error, they are dependent on the quality of reagent which is used during the pharmaceutical analysis. For example, some reagents are supplied in impure form and some are pretended to be absolutely pure, but they are not actually pure. So when these reagents are used in pharmaceutical analysis, they cause the errors. Now constant errors. Remember, we are talking about the determinate errors, and these determinate errors, these are the avoidable errors which we can avoid by taking precautions, by calibrating the instruments, right? By taking the high quality of the reagents, right? Now the constant error. The constant error, they remains constant throughout the pharmaceutical analysis, irrespective of the amount or the volume of the sample which is used. For example, it's for example, in case of titration, which we learn in coming classes, in the titration, the end point appears, for example, at 5 ml, 5 ml of the titrate. But for proper visibility of the endpoint, because that's the change in the color or the pH, if we add 0.1 ml, then it would be zero point 0.1 ml instead of 5 ml. Now, in again, so what is the constant error? That is zero point 0.1. At 5 ml, the endpoints come in the titration, but it's not so visible. So we add zero point 0.1, some drops of 3, 4, 5 drops of the titrant, then it becomes 5.1 ml. So now the endpoint comes at 5, but it is more visible at 5.1. So this is a constant error, 5 and 5.1. This 0.1 is a constant error. The next is proportional error. Proportional error, it increases in the absolute error. This, for example, 5.1 ml instead of 5, 10.2 ml instead of 10. These are some of the proportional error. We want to, that may be because of the instrument error, or that may be because of your way of taking the sample through the burette, through the conical flask, etc. These are the proportional errors. Now, errors in the method. These are the inherent in the method and they cannot be changed. These errors occur due to the selection of the wrong method. For example, if the synthesis of one product takes place in 3 hours, but we have given 2 hours, then what will be the final product? The final product will be defective. So this is the error in the method. So these are some of the determinate method which we can, some are avoided, many of them they are avoidable. However, we can avoid all of them, but some are not avoidable, like the constant error, like the error in the method. If you choose the wrong method, you have to again choose the right method. Now next is indeterminate errors. These indeterminate errors, they are accidentals, or they are the random errors. They may or may not be known to the analyst. The analyst has no control over such type of errors. This may be because of the problem of the sample, of the instrument, and there are multiple factors which cause this indeterminate error. And that's why indeterminate, that means it cannot be determinate. We cannot determine these errors because they may or may not be known by the analyst. So for this, what we generally do, for example, if there is an error in the result, so then we take the replicate of the uh, replication results. That means, for example, we take a single result, we perform a method in a single way, so then we do in multiple ways, in triplicate, in duplicate, 2 times, 3 times, to minimize these errors. So these are the indeterminate errors. Now, what are the absolute and relative errors? These absolute and relative errors, absolute, which is calculated by measuring the difference between a measured value and a true value. It is a part, obviously the determinate and determinate comprises of all these errors, but specifically if we say what is absolute and what is relative, so absolute is measuring these errors by the difference between a measured value and the true value. That is same, which is an error. So what is relative? Which is the relative is the absolute error divided by the true value. This is the percentage values which is we have gone through in the first slide. Now the next is measurement errors. What are these measurement errors? The cause of these measurement errors are numerous, and their magnitude they are variable. This lead to the uncertainties in the reported result. All measurement process in which we measure something, they are subjected to measurement error that affect the numerical data which arise from a variety of sources. To control these measurement errors, we use the statistical methods of the data analysis, and some are of the chemometric analysis. So whether it is the measurement error is it is a reading of a burette or a thermometer, weighing a sample or timing events, or the electrical signals, so there will be always an inherent variation in the measured parameter. The next is the accumulated errors. These accumulated errors, these are the where the several different measurement are combined to compute a overall analytical result. These errors, they are associated with each individual measurement contribute to a total or accumulated errors. That means they are the different measurement errors when they combine, so that's why they are known as the accumulated errors. Now what are the sources of these errors? The first is improper sampling. While we are taking the sample, while we are weighing the sample, the improper sampling cause the is the one of the source of errors. During sample preparation, what volume we are taking, in which glassware we are making, the glassware must be calibrated like this. So the errors which occurs during the sample preparation, improper and or careless analysis. That means improper, do not take precautions, do not emphasize on calculation, and it is a kind of careless analysis. Then the errors are may occur. For example, you are using a spatula, the same spatula for two types of the compounds. You are using a single pipette for two types of the liquid or the solvent. So there will be a contamination errors. Improper function of the equipment. That means the equipment is not working properly. The equipment is not giving good result. It's not calibrated. That means it is not giving the good result as well as not properly functioning. Wrong data and improper observation. If you observe improperly, if you get the wrong data by the because of due to some of the fluctuation in the voltage by the sample problem, right? So this is also one of the source of error. Wrong calculation. If you use the wrong formula, right? So then this will be the source of the error. Wrong method selection. If you choose a wrong method selection, you have to choose the acid base titration, but you have to choose the non-aqueous titration, right? So there might be chances that this cause the some of the errors. Improper handling of the material during transport and or storage. So handling of the material during transport improperly or improperly storage can also cause the error. Now, what are the methods which are used to minimize these errors? So the first method is proper calibration. Proper calibration of the glassware. The glassware must be of good company. Borosill, pipette, burette, weights. balances, instrument, they all are must be calibrated. So there are methods, there are procedures to calibrate the instrument, to calibrate the glassware, etc. The sixth is the correction factor that must be added to the result. If there isn't any correction factor, that means the instrument they are not calibrated and there is some correction in the burette, in the pipettes, so that must be added to the into the result. Next is by running the blank with the sample. While we are working with the sample, obviously we are working on an analyte, the analyte and a, a solvent. This solvent without the analyte is known as the blank. Might be possible that it contains some chemical, it contains some impurities, it has its own kind of results. So that's why we use the blank, so that when we add the analyte into it, then we can minus the blank from this, which may be a source of the error. The blank solution is defined as the solution by omitting the sample addition. So the blank and the sample solution, they are carried simultaneously to obtain the accurate result. Next method to minimize the error is running the standard solution. We have an analyte, but to whom we are going to compare this analyte? So we must have a standard solution along with the sample unknown solution. We want to quantify a substance, we can quantify, but we want to identify a substance, so we must be a standard solution for that. We are going to calculate the percentage purity, so for percentage purity we must have a standard solution, so that we can compare the unknown sample solution quantity or identity with the known standard solution. So in this, the weight of the unknown sample solution is determined, and then and compare it with the standard solution. So there are some other methods of minimization errors, just like using the independent method of analysis, running some parallel determinations, right, and some using some standard addition methods, etc. So this is about the errors, types of errors which are avoidable, unavoidable, and the minimization of these errors.